Recording.
Okay, so I really quickly just want to go over the different bond types and give you a conceptual basis for why certain bonds are stronger than others, and clear up some confusions about covalent versus ionic bonds, because a lot of students come in saying, well, I thought ionic bonds are stronger than covalent, so why are you guys telling me covalent is stronger than ionic? So what we're going to do over here is we're going to talk about the different bond types. So the stronger bonds or the more stable bonds are at the top of the list. The weaker or less stable bonds are at the bottom of the list. And I want to add a caveat because a lot of students will come and ask, oh, I thought that ionic, we say in our general chemistry classes, they are stronger than covalent. And yes, they are. So if I actually put a 0 over here, so if we're putting like the strongest one, so ionic is the strongest, but this is whenever it's not in a solution. So if this is like, for example, in solid form. Okay, so an ionic bond, like if it's in the air or something and not in solution, we're going to say that ionic bonds are stronger than covalent. But what happens, for example, if you put an ionic bond like salt, NaCl, into solution? Okay, what happens is it dissociates. It's an ionic bond. So what we're going to do over here is, because it's a biochemistry class and everything, life happens in water, that's why we tell you guys that covalent bonds are stronger than ionic bonds. It's just for the purpose of this class, but yes, you're right that ionic in solid form is stronger than covalent, okay? But yeah, what we're going to do over here, because we are doing our biochem class, we're going to say covalent is stronger than ionic. Okay, now what we're going to do is we're going to say, okay, covalent is stronger than ionic, and an example of that is a disulfide bridge, okay? Next, we're going to go is ionic bonds. So notice how it's a full negative charge interacting with a full positive charge. And then from there on, dipole-dipole is partial charges. Dipole-induced dipole is also partial charges. And induced dipole-induced dipole is also partial charges. So a way that you can categorize these different bonds inside your head, and I think it's a nice segue to your physics classes, is if you remember from our physics class, we learned that, okay, Coulombs Law, it was equal to, if I can bring this up, okay, we said that Coulombs Law was equal to FKQ1Q2 over R squared. And what this means is that, notice how this is the attractive force over here, the F is the attractive force between two things. So we're saying that if we make the magnitude of our charges larger, if we increase these, we're going to increase the attractive force. And if it has a larger attractive force, it means that it is a stronger or more stable bond. So notice how, because ionic bonds have full charges, they're going to have larger charges over here, which increases that attractive force, meaning that they're going to be stronger bonds, they're going to have stronger bonds, and they're going to require more energy to break compared to dipole-dipole interactions or dipole-induced dipole or induced dipole-induced dipole interactions, okay? So that's how you're going to do it. Then you're going to go to dipole-dipole interactions, and there's two types, so H bonds fall within that category, but because these are permanent dipoles, okay, because these atoms are connected to electronegative atoms and it produces larger dipole moments or larger partial charges, because these partial charges are a little bit, they're smaller than full charges, but they're a little bit larger, they're going to be the next strongest type of bond. And then everything below that, the partial charges get smaller and smaller. So for example, induced dipole, they form the smallest partial charges, and that's why we say that they have the weakest or least stable type of bonds, okay? So again, what I'm going to say over here for dipole-dipole or H bonds, so H bond is a type of dipole-dipole bond. So the way that you're going to know that you have that is you have an electronegative atom over here that forms a partial negative charge. And then if you remember from our OChem classes, there's a resonance structure over here. So this is partial negative, that's partially positive. And this partial negative interacts with the partial positive carbon, okay? That's a dipole-dipole interaction. Okay, now if we're going to look at an H bond, what we need for an H bond is a hydrogen connected to an electronegative atom. So the electronegative atom withdraws electron density from the hydrogen to make it partially positive, and then the partially positive hydrogen will then interact with another electronegative atom. So I drew the water over here. Notice how this is electronegative, and then the partially positive hydrogen is interacting with a partially negative oxygen, and that's the H bond, okay? Then we're gonna have a dipole-induced dipole interaction. So a dipole has an electronegative atom, and that's what makes it a dipole. Induced dipole means that everything has roughly the same amount of electronegativity. So we're gonna say that it's an induced dipole, meaning that it has to be induced within the molecule. It's not, it doesn't have a permanent dipole such as those molecules that, like for a dipole-dipole interaction, that, like for example, like water, where there is a permanent dipole associated with an electronegative atom. Okay, so the way that you know that you have an induced dipole is if I drew out all the atoms. So notice how if I had an oxygen connected to, for example, a carbon, this produces a dipole moment, because this acronym, all it's showing you is that these are more electronegative, these are less electronegative. So that means that the ones on the left withdraw electron density. So this is going to be the delta minus, this is going to be delta positive. So the electrons are kind of withdrawn to over here. But notice how for the induced dipole, we have atoms like a CH3 or hexanes or anything that's nonpolar, okay? We're saying that because their electronegativities are roughly the same, okay, there's not going to be a really large charge separation, so that it's kind of like a smaller partial charge, and that's why we say it's a temporary partial charge and it's an induced dipole. Okay, so what we're going to do over here is that, because again these are closer together, we're going to say it's a smaller partial charge and it's going to form a weaker bond. Okay, and then the weakest bond is an induced dipole bond. And notice how again 2 CH3 groups, both of them have electronegativities that are very similar. And I know on the study questions, there's phrasing that says transient asymmetric what the study question is trying to say is that if you looked at the electron cloud surrounding these molecules, okay, so the electrons are freely floating around these things at all times. But at certain points in times, notice how one side, if we took like a snapshot, notice how one side of this molecule could have a little bit higher electron density. Notice how the left side has a little bit more electrons, and it's just random. Like sometimes it's just because the electrons are freely floating. At a certain point in time, you could have more electrons on one side. So that means that this side could be and it's a very small partial negative, because again, we said that this is an induced dipole. It's not a permanent partial charge separation. So we're going to say it's a small delta minus. And then what could happen on another molecule is the same thing could happen, but in the opposite way. So imagine that in a certain point in time, all the electrons come to one side and very few are over here. So this side will be partially negative, and because that side's partially negative, that side's partially positive. And these partial negative, and notice how this is partial positive, this is partial negative, they can interact to form a very weak transient but induced dipole bond. Okay, it's a bond nonetheless because there's an attraction between opposite partial charges. Okay, so the idea here again is the strongest bonds, covalent's the strongest, but then following that, the larger the partial charges, Ionic has full partial charges. Everything after that is smaller partial charges, to the point where when we get to induced dipole, we have the smallest partial charges, and these form kind of temporary interactions based on the differences in the electrons in the electron clouds surrounding the molecule.